Okay, guys, big apology. Just realized that when I was doing the electron configuration, noble gas electron configuration of sodium and chlorine, I have no idea why I did that, but I wrote neon and then I wrote 1s. Obviously, it's 3s, so sodium is neon 3s1 and chlorine is neon 3s2, 3p5. So I do apologize. Hopefully you realize that, I made a mistake and I don't get a 17 million emails telling me you messed up. But if you are going to send me an email telling me I messed up, that's okay. I apologize. Anyway, that's what this was. All right, so let's move on and we'll do the electron configuration of ions. Now we know how to do the electron configuration of an atom. We learned that in the last chapter. Well, what's the electron configuration of the ion? So what we're going to do is when you are losing or gaining electrons, you always lose or gain from the outermost, in the outermost shell, okay? So let's say you've got sp-d electrons, you always lose the p and the S of the outermost shell before you lose anything from the D. Okay, so let me show you what I mean by that. So let's say we've got iron. Let's do the electron configuration of iron. So looking just regular iron, we're not talking about the ion. So we can see where iron is. So we can write argon, and then 4s2. And then we've got 1, 2, 3, 4, 5, 6, 3d6. Okay, now you know that iron can exist as Fe2 plus and iron can exist as Fe3 plus. Remember, it's a variable charge ion element, so iron can exist as two different charges. All right, so how do we do the electron configuration of this first guy? Well, right away, you know you have to remove these two. So iron 2 plus, or the ferrous, iron Roman numeral 2, is argon 3d6. Okay? Well, what would 3 plus be? Well, you're going to lose these two, and then you're going to take one away from here. We don't have any p's to remove, so we're going to take one away from here. So then it would be argon 3d5. You see what we're doing here? Okay, so we could do that for another one. Let's say we've got copper. Do you remember that copper was one of those elements that's in that 1b zone? So let's go ahead and write the copper electron configuration. Copper is argon. Remember, it was 4s1, 3d10. You guys remember that? Okay. All right, so copper can exist as copper plus or copper 2 plus, right? Cuprous and cupric. So what would cuprous be? You just remove this guy, so it'd be argon 3d10. And then cupric, you remove this and then 1 from here, and that would be argon 3d9. Okay, let's do lead. So lead, we know, is xenon, and it would be 6s2, 4f14, 5d10, 6p2. Okay? Yeah. What's the outermost shell? What are the valence electrons? These guys. Okay? So lead ion exists as +2 or +4. So Pb2 plus, which is plumbus, you remove these two guys. So that would be xenon, 6s2, 4F14, 5D10. And you can flip them around and put the 6s2 out here just to show that it's the valence electrons, but it's fine like this. Now, obviously, PB 4 plus. So notice what I did over here. I removed the P before the S. So if you have P and S in the same shell, those are your outermost electrons. You remove the P, then you remove the S, and if you still need to remove some more, then you remove the D, okay? But you don't over here. So for this one, it's going to go xenon. You get rid of these guys, and it'd be 4F14, 5D10. Okay, so that's electron configuration of ions. Now let's talk about ionic radii. So we're talking about the radius of an ion, not the radius of an atom. We already know the trends for the radius of an atom. Let's talk about the trends for ions. All right. So let me go ahead and write this thing here. In general, across any period, because it's a little tricky, it's not as straightforward as with atoms. Across any period, the cations decrease in radius. So as you go across a period, the cations decrease in radius. So if you're looking at, for example, sodium, magnesium, and aluminum. So they're in the same period. Sodium, magnesium, and aluminum. They're in the same period. They're going to decrease in radius as you go across, meaning that sodium has a bigger radius than magnesium, which has a bigger radius than aluminum. And you can kind of understand the reasoning behind it because of that whole nuclear charge thing. Do you guys remember that? The more the protons, the more it pulls at those outermost electrons. So basically your aluminum is going to be smaller than this, and this is going to be smaller than this. All right, now we continue the story here. When you reach the anions, there is an abrupt increase in radius. Why is that the case? Because these cations, they are losing electrons to look like the noble gas in the period before. But the anions of that period are actually gaining electrons to look like the noble gas in that period. So, for example, sodium, magnesium, and aluminum want to be isoelectronic with neon, but in the same period, you've got phosphorus, sulfur, and chlorine, and they want to be isoelectronic with argon, and argon has a bigger radius than neon, right? So there's going to be an abrupt increase for the anions in that period, and then the radius decreases again. Meaning, if you're looking at the anions of period 3, so the phosphide and the sulfide and the chloride, okay, so these 6 are all in the same period. They're all in period 3. It says here that these guys are going to be much bigger than these, because always anions in the same period as cations are always going to be bigger than those in that period. But it says that as you go across, it's going to decrease again, meaning that the phosphide is bigger than the sulfide, which is bigger than the chloride. Why is that the case? Because this has a bigger nuclear charge, it has more protons, it's pulling at those electrons more. So it's making it smaller radius. Okay, so this is an important concept. Now let's move on to isoelectronic series and the radius, how we can compare the radius of an isoelectronic series or an isoelectronic group. What is an isoelectronic series or group? That's a bunch of atoms or ions that have the exact same number of electrons. So they're all isoelectronic with a specific noble gas. So let's take a look at a series here. Remember, they all have to have the exact same number of electrons. So let's go ahead and do an isoelectronic series for argon. All right. All right. So we need everybody who's got the same number of electrons as argon. So we've got phosphide, we have sulfide, we have chloride, we have argon. These are isoelectronic. We have potassium, and we have calcium. All right, here's my series. This is an isoelectronic series. Everybody can see that? You can see they all have the same number of electrons. Let's write down the number of electrons they all have. This has 18 electrons. Phosphorus normally has 15, picked up 3 to become 18. Sulfur normally has 16 electrons, picked up 2, it has 18. Chlorine normally has 17 electrons, picked up 1, it now has 18. Argon always had 18. Potassium normally has 19 electrons, lost an electron, and now it has 18. Calcium normally has 20 electrons, lost 2, now it has 18. So they all have 18 electrons. Okay, these are all electrons. Now, let's take a look at their protons, okay, because that will help us explain the trend in the series. Phosphorus has 15 protons. Sulfur's got 16 protons. Chlorine has 17 protons. Argon's got 18 protons. Potassium, it's not in the same period, but they are isoelectronic. Potassium's got 19 protons. And calcium's got 20 protons. All right. With your knowledge of effective nuclear charge, meaning the more the protons, the more it's going to pull at those outermost electrons and make that radius smaller. Which one's got the most protons? Calcium's got the most protons, right? So if calcium's got the most protons, it's pulling at those electrons more, so probably calcium is the smallest radius of the bunch. Which one's got the least number of protons? You've got phosphorus. Phosphorus has the least number of protons. So in this isoelectronic series, we're going to say that the phosphorus is going to have the largest radius, right, because it has the least nuclear charge, and calcium, from all of this, has the smallest radius because it's got the most protons and it's pulling it in. We can do this easily when we compare an isoelectronic series. So we're going to say the phosphide, larger radius than the sulfide, which is larger than the chloride, which is larger than argon, which is larger than the potassium ion, which is larger than the calcium ion. Okay, so that does it for the isoelectronic series. Just always think that this one has the greatest nuclear charge. Most nuclear charge means most protons. Most protons. Oops, I'm messing up a lot. Pretend I didn't say that. This has the greatest nuclear charge. It has the most protons, so it has the smallest radius. Okay? Biggest effective nuclear charge is the calcium, most protons, smallest radius. This is an isoelectronic series. Okay, there you go. All right, so next video we'll be dealing with covalent bonds. So I think we are done with ionic.